Thanks to the organizers for the invitation for this wonderful event. So fortunately, I'm lucky to and spend a couple of months to work with the girl in my first sabbatical time. Is in 2008, long time ago now. Okay. So what I'm going to talk today is about the spatial temporal and dynamics of the diffusive Mussel-Algae model near Turing-Hopf bifurcation. This is the joint work with Yuan and Heping Jiang and Chenxin Liu in China. So here's an outline. So after the introduction and the motivation, we'll talk about the dynamical analysis for the Mussel and Algae model. Well, our focus is on the Turing-Hopf bifurcation and analysis. Well, before that, we'll go through just a quick review for the bifurcation problem of reaction diffusion system and the normal form theory. Actually, in this morning's talk, Gugni and somebody else talk about the bifurcation, right? I know there are lots of experts here. Yeah. And so after we know the method of normal form and the sentiment for the method, then we can, got the bifurcation and normal form for the and Turing-Hopf bifurcation in this model. Then we can classify all the dynamic behavior, or say the spatial-temporal patterns in each region. And well, all of us know that most of the bifurcation analysis is just local, right? Just very few work is about the global bifurcation. So if the parameter values is far away from the bifurcation point, so what's happened? Normally, it's more complicated. Yeah. So we just do some numerical simulation to see the behavior change. Okay. And later on, we just do a quick, discussing about the influence of the advection in the model. Yeah, this is a reaction diffusion model could include in the advection, right? And well, I finished talk with some conclusions. Okay. So here, okay. So this is the image of the patterned muscle band. So this one actually is composed of the larger concentration of muscles. Right? All the lady with the regions is almost zero muscle. Right? Well, so this actually the spatial pattern is interesting and is actually has attracted many scholars. Well, from dynamical also actually also from this this image, we can see what the bands form the perpendicular to the direction of the tidal flow. And also, in fact, it can be seen it's slowly moving on, in the upstream direction. Yeah. So it's interesting pattern, right? So many people, want to see why there's this kind of pattern. Well, for us, from dynamical point of view, we'd like to know, so what is the mechanisms for such, spatial pattern formation? Since all of us are mathematicians, so we know mathematical models is the good way, right, to do like the theoretical mechanisms for the pattern formation. Well, we know there are lots of models from just a different view, right? Different view. Well, in this, tons of models, actually seems like the reaction diffusion equation is more reasonable to approach the reality, right? Because it's including spatial and the time variations, right? So normally, the reaction diffusion equation is served as a like the simplified model in many applications in biology and chemistry levels. And actually, okay, so in the literature, there are some work for the theoretical investigation in the Mussel-Algae models. And one of the important work is from in 2005 from the Wendell Cooper. They just produced the simple model to discuss the pattern formation process. So it's a very important one. And then later on, just by using the numerical continuation techniques, so in this paper, they found the periodic solution together or coexistence with the homogeneous steady state solution. Well, this one, the proved it's unstable. It's unstable due to this, differential flow induced. And in this paper, they just use the geometrical, like singular perturbation method to analyze the waveforms and the oscillation behavior. And so then in this one, actually, is considered the reaction diffusion and also the advection. Well, when the advection is like the larger than the diffusion scale, so in this one, they proved they found actually the family of periodic wave solutions. Okay. Well, for all this works mainly based on this model, Okay. Well, in this model, it's a little bit different. This model, they just consider, for the algae and the mussel, algae normally it's in the upper floor layer of water, right? Well, the mussel is in the like the benthic water, so they introduced the water depth, okay, and then just modify the model in this one. So M is a mussel and A is an algae, and there are many parameters. So all the parameters of this biological interpretation we just give it here. Okay, give it here. Well, and for this model, in general, there is like the diffusion term and the advection term is here. Okay. And for this model, actually, we can do the rescaling to simplify the model first. Right? So after the rescaling, we can got this model. And so in this in their paper, they just discussed this model and and analyzed the Turing patterns. Okay, they just use the weakly nonlinear diffusive instability method. Okay. Well, so
a little bit further away.
Okay.
Very sensitive.
Yeah. So I just okay. And actually, in this work, although they're including the advect term, right? But it said that from some of the experiments, the people can see that the mussel can actually actively move both within and between the clusters. So what does this mean? Means actually in the small scale space, actually the effect of the advection of the tidal flow on the mussel bird actually is small. It's small. So in most of the work so far, although the model has the advection term, but most of the work just assume V is 0. Of course, it's easy to analyze, right? And also, from the biological background, it's no big difference if it's in a small scale space. Okay. And so in our model, we also assume V equals 0 here. Okay, equals 0. So the main purpose of our work is just try to using the normal form and the center manifold theory to analyze the Turing-Hopf bifurcation. So which we know this is like the coordination 2 bifurcation. Coordination 2 bifurcation is like the interaction of Turing bifurcation and the Hopf bifurcation. Okay. So first, we just consider the local system, means do not consider the diffusion term first. Okay. So this is a very simple ODE model. It's a very simple ODE model. And so in this model, it's easy to see the boundary equilibrium always exists, and it's stable when R is between 0 to 1, well, becomes unstable when R is greater than 1. Right? It's easy. So besides the boundary equilibrium point, we can see the positive equilibrium point could exist under certain condition, like H1 or H2. Well, remember in this scaled system, there is 3 parameters, R, gamma, and alpha, right? So we can see the existence of the positive equilibrium actually only relates on the alpha and R. That means, you know, any gamma doesn't affect the existence of the positive equilibrium, but it affects its stability. So we can prove. So actually, for this positive equilibrium, it's always unstable, which is a saddle point under the H1 condition. Well, if H2 and with H2 condition, actually this one is stable for some gamma. Well, for some others, it's unstable. Well, so in that way, Hopf bifurcation is possible. Actually, we can find this relationship with these 3 parameters. Well, so in this one, we can see, so this is in the R and an alpha plane. So for R1 and R2, the positive equilibrium exists. Well, in this part, R1 is unstable. In R2, it depends on the location of this green curve. It could be stable, could be unstable. Okay. Well, so if we just fix, we like to see the 2-dimensional is better than to view in 3-dimensional, right? So if we fix the parameter alpha, then we can find the, so the relationship and also the Hopf bifurcation can occur at these 2 particular R. So actually here shows, so this is like the curve, right? So this is R1 and R2. So this is for the local model, which is quite simple. Well, then later on, we consider the diffusion, reaction diffusion model. So with diffusion, actually, the previous positive equilibrium becomes what? Becomes a spatially homogeneous state. Okay. Well, remember previously we provide some condition for his stability. So if without the diffusion is stable, but when there is a diffusion, it becomes unstable. So that means it's like the diffusion-driven instability, right? Which is called the Turing instability. So in this one, actually, we can discuss again for his characteristic equation, because the involvement of the diffusion, so the characteristic equation has like the sequence of that, right? Because K is a waveform. So in this one, it's easy to see this positive equilibrium, it's locally asymptotic stable if both of these, coefficients are positive. Otherwise, if one of them is negative, then it becomes unstable. So which means it's possible to have the diffusion-driven instability, right? So that's our main purpose in this project, okay? So actually back to this model, for fixed alpha, so first we know it's the Turing-Hopf only occur, at least has a Hopf bifurcation, right? Besides Hopf, it's possible to have the Turing, instability. So in this one, actually we can find, this 2 red lines are the Hopf bifurcation. Well, this black curve is a Turing one. So this shaded region is a Turing instability. Okay, so we can see this points, the intersection point of this is a Turing-Hopf bifurcation under the if the transversality condition holds, right? So what kind of dynamical behavior it has just near this point? So in that way, we have to consider or to find his normal form in his center manifold, right? So before we go through the detail to that, we just go and do a quick review on the recent studies on the bifurcation in for reaction diffusion equation. Okay, so for Hopf bifurcation, there are lots of results so far. Hopf bifurcation we know is coordination 1 bifurcation, right? And so for the reaction diffusion, different boundary condition, they may have different behavior. Right? Well, for the Neumann boundary condition, I just list a bunch of works here. So yeah, I know Xinfu and Shi Gui and Jian Hong, they have done some work. Yeah. So for the Neumann boundary condition, people many working on the existence and for the stable spatially homogeneous periodic solution for Hopf bifurcation. And well, with the diffusion condition, yeah, which we know is different. So there are some work, even including delay in the model. So in these papers, they discuss the delay-induced, stable, spatially inhomogeneous periodic solution. Well, this is for coordination 1. Well, for Turing-Hopf bifurcation, it's coordination 2 bifurcation is more complicated. And again, for the different boundary condition with delay or without delay, they have some works as well. And again, so in this one, because the Turing-Hopf, so we are more interested in the stable spatially inhomogeneous periodic solution. And the difficult one is about the derivative condition. So in recent paper of Wei Huajiang and Junping Shi, they have they provide the general algorithm, but still cannot find the explicit form for derivative condition. Well, besides this one, and also for the spatial and resonant bifurcation, although it's still called coordination 2, but it's much more complicated, for the analysis. So there are some works as well. For many, it's for the numerical simulation. No, not so much about the theoretical analysis. Well, for the derivative condition, even more. I don't know is there any recent work or not yet. I cannot find that. Okay. Anyway, well, for the basic idea of the normal form and the center manifold is just try to do the phase space decomposition first, right? So we need to get his center manifold. Then, so for this one, this Z equation is the center manifold. So this comes from the space decomposition. Well, after this one, then we try to simplify it more. So we just using the sequence of neo identity and transformation to reduce the terms in the center manifold as much as possible. So what kind of terms we can remove to keep the same dynamical property? So this is the idea in normal form computation. So we use the operators like this. So this is like the Lie algebra to remove. We can remove actually all the non-resonance terms just to keep the resonant terms in the normal form. So then this one get more simple to do the dynamical analysis. Okay, so this is the idea. And then for the reaction diffusion equation. So first one, again, we need to do the space decomposition, right? And for the Turing-Hopf bifurcation, this is our main purpose. So for this one, we assume because there is a Turing-Hopf, right? So we assume what? We assume in the characteristic equation, so there is a like the pair of simple purely imaginary eigenvalues, right? In one of these factor, we suppose we can factor that, right? Well, besides this one, there is another one has a simple zero roots, which means corresponding to the the Turing bifurcation. So the interaction of that, we consider the the Turing-Hopf. Okay. Well, of course, we assume all the other roots have negative real part, right? So if there is a positive one, then the whole system is unstable. We don't need to do that. So in that way, we can find the Turing-Hopf bifurcation, the normal form for Turing-Hopf bifurcation has the terms like that. So this is just cut to the third order. So this is linear part, this is second order part, and the higher order part, right? So for this one, actually, we can also change to the cylindrical coordinates, and also we just try and truncate to the third order. Normally, if the coefficients in the third order is non-zero, then it's enough. Okay. And so this one actually for Turing-Hopf is related to three-dimensional, but we can just ignore the Azimuth form. So then just keep this is like the z-axis, and this is like the radius in the polar coordinates, right? So for this one is here. So although it looks like simple, but the computation is tedious. Yeah, it's tedious. But anyway, so back to our model for the fixed alpha, we know when there is a Turing-Hopf bifurcation, right? Then using this algorithm, we can find or compute his normal forms is given in this. So that means actually, for any system, if we know when there is a Turing-Hopf bifurcation, and using our algorithm, we can find the exact form, okay, explicit form. So based on this explicit form, we can do the, we can analyze the spatial temporal patterns in each part explicitly, okay. Well, here epsilon 1, epsilon 2, just the perturbation. We use like the we introduce the perturbation in the mu, which is related to the diffusion term, and R, okay, and R. So based on this one, actually we know for this model, the origin is always the equilibrium point, right? The origin actually is related to the positive and spatially homogeneous steady state. Besides that one, it's possible to have what? To have the boundary, an equilibrium point in this normal form, even for rho is 0 or R is 0, both are possible. So besides the boundary equilibrium, it's also possible to have positive equilibrium as well. So there are different kinds of equilibrium point. Well, so for this, related to the epsilon 1 and the epsilon 2, so they can determine the 4 critical curves. So one is this, H actually means epsilon equals 0, epsilon 1 is equal to 0, or like the T and T1 and the T2. So these are 4 critical curves. Well, these curves actually separate the whole epsilon 1, epsilon 2 plane into 6 different regions. Well, in this region, each one actually have the similar property. So this is like the bifurcation diagram, and also including the phase portrait in each part. So after we know this, actually we know the whole dynamical properties of this model, right? So actually we can see, for example, for the D1 region, so in D1 region, only one equilibrium point, which is just the origin, right? Means only the positive. In the original equation, it's positive equilibrium and steady state, right? Which is stable, right? Which is stable. Well, cross this one, besides this one becomes unstable, but the stable, boundary equilibrium is here, right? So this boundary is in R, right, in R axis. That means in the original system is what? The original system means there is a stable, spatially homogeneous periodic solution, right, which is stable. Well, so for this one, we see, and it's different from this as well, right? Besides these two, there's two more boundary equilibrium in this, and axis, right? So this two is related to the inhomogeneous steady state. Well, for this one, besides these two, there are two more positive equilibrium points, right? So these two actually, with respect to the original system, is related to what? It's related to the spatially inhomogeneous, but it's a periodic solution. So this one is different as well, from this as well, because here there is no this boundary, right? So up to this one, so all these are boundaries. So it's different region, different behavior, right? Different behavior. Actually, we can see some numerical simulation. Well, so the first one, we see the stable state, right? So stable steady state or stable periodic solution, right? Or stable what? We have actually here we have 4 types of stable solution. One is what? One is actually is the stable homogeneously and steady state, right? Steady state, which is this. Which is this? Well, well, for this one, it's stable, but this is a stable what? Stable, spatially periodic solution, right? Periodic solution, which is corresponding to this periodic. Excuse me. Well, and for this one, this is also so this one is stable, right? So it's local stable. Okay. This stable is what? This is not in. This is still in an axis. Okay. So for this stable, for this two, stable is what? This one is like the stable, spatially inhomogeneous periodic solution. Okay. Well, for this one, so this is stable, inhomogeneous and inhomogeneous periodic solution for this and this as well. Well, this one is different, right, from these 3 types. This two is similar. This two is similar. Well, this one is what? This one actually is corresponding to this. Is inhomogeneous, spatially inhomogeneous, but it's steady state. It's steady state. So they have different stability for this. Well, besides these 4 types of stable solutions, actually we can also see 3 types of the transaction, right? Because we can see here, for the transaction, so first it's like the unstable, but it's in the boundary of this, right? Then move to this one. So how's the transaction in this? So actually, so this is a whole picture from this transaction. So this is from unstable, spatially inhomogeneous steady state to the stable, spatially homogeneous periodic solution. Well, if we just and separate the starting part and the ending part, we can see more clear. So this is the starting part. So this is like the inhomogeneous spatially, but because it's unstable, right? If it's stable, it's just like the horizontal lines. But it's unstable, so we can see what? So this is like the start, like the transaction, and this is the ending. The ending one, we just got the spatially, stable, homogeneous periodic solution, right? So this is one of the transaction. And the second one is also like the transaction, but from well to well. We say it's from unstable, spatially homogeneous periodic solution to what? To stable, spatially inhomogeneous periodic. So from one periodic to another one. Okay. So again, this is the whole picture. So this is the starting part. So it looks like the it looks like it's spatially homogeneous, but because it's unstable. So finally it moves to this inhomogeneous periodic solution. So this is, so actually the previous one is for like 2-dimensional, right? So we can also show a picture for the 3-dimensional. Yeah, we can also see this change or this transaction. So besides this one, there is another one. The other one is what? The other one is from the unstable and spatial inhomogeneous steady state to what? To periodic. But this periodic is stable, spatially inhomogeneous periodic solution. So this one actually we can see what. So first, because it's unstable, so it's not like the stable and inhomogeneous steady state, right? Steady state means the horizontal lines, but finally it goes to this way, So this is for the Turing-Hopf bifurcation. So just close to the bifurcation point, right? Well, how about if the parameters is far away from this kind of special points, right? So in that way, it's more complicated, right? Actually, I don't think we have like the theoretical way to do the analysis or the prediction, but from a numerical way, we can see some change. So for example, we just fix epsilon1, then we change the value of epsilon2. Okay, so in that way, actually we can see what? We can see the dynamics change. So if we decreasing the value of epsilon2, the change is what? Is from like the spatial homogeneous periodic solution. So for this, if for certain value of this could be stable, but the increase of this one actually is changing to this. It's changing to this. So it's different. Epsilon2, we got a different, the inhomogeneous steady state. But we can see the strip has like the white and strip or leather strip. So because it's far away from that, this is what we can see. Well, this is for the far away from the Turing-Hopf point. Well, how about the advection, right? Because the previous one, we suppose we ignored the advection, right? Well, with the advection, what's happened? So not so many results. Just recently, I know, actually one of my collaborators with another of his colleagues found some result. So in the model of the reaction diffusion with diffusion and advection, but it's just for very special model. Okay. So well, numerically we can see what. So with the increased value of the advection, so previous one is V is 0, but the increase the value of the advection, we can see what looks like the introduction of the advection. We can see just destroy the stability. So for this one, it's stable. Looks like a small one is stable. Increase a little bit, then just got this. It's unstable solution now. So similarly for this, yeah. So first one, if no of this, which we can see, we can got the inhomogeneous periodic solution. But with this one, then we cannot see anything, right? It looks like it's unstable now. Yeah. So this is just for the the main work. So yeah. So actually for this one, to do this bifurcation analysis, actually we know we can. So probably it's easy to understand the real natural world, right? will let you work. So we can determine the spatial-temporal patterns explicitly. So it's interesting to find some like the different stable, homogeneous, inhomogeneous periodic solutions and steady state. Well, in this one, actually, for the spatially, stable, spatially inhomogeneous solution is more interesting because it's just the result of the interaction of Turing model and the Hopf model. Okay, so and also the three transactions, right? Well, just want to mention, for the how to predict the real system or his pattern for the models with both diffusion and advection. So I suppose it's one of the future topic. That's it. Thank you.
Well, good timing.